So, Unit 5, Day 2. Right? So, when we find the area under a curve by adding rectangles, which is LRAM, RRAM, or MRAM, the answer is called a Riemann sum. A Riemann sum. So you might hear, that term thrown around in college. All that is it's the area under the curve when you add rectangles to fractions. Now, the width of a rectangle is called a subinterval, just like on your drawing. And the entire interval itself, not the subintervals, but all the intervals are called, well, it's right there, partition. Subintervals do not all have to be the same size. This is where it gets tricky, but you won't have to worry about that, because this is like introduction to stuff, okay? So, let's take a look at this. Anyways, Leibniz introduced a simpler notation. Now, this thing here that Riemann came up with, Riemann sum, it's the limit as n approaches infinity of the summation from k starting at 1 to n, which would be infinity, of the function c to the lower, what do we call it, subscript k delta x means a change in x. Okay? That turns out to be a bear. Yeah. So, here we go. Alright? Thank you, Gottfried. Now, I think that was Leibniz's first name. So I'd say thank you, Gottfried. And I wonder if it's a G-O-T-F, like Gottfried or Gottfried. I don't know, but it's right there. Okay? So thank you, dude, because we can now take this big mess, which I showed you the birth, I guess, of this, and now just use this right here. And d of x, like d of y, with d of x, when you find the change in y over a very small change in x, you are going to find ultimately the integral, or integration, which is the reverse of derivative, with a very small change in x. Then it becomes almost insignificant, and it's just notation. Okay? Let's play around. All right, so let's figure out what each one of these means. First of all, that straighten up S type thing, that's the integration symbol. That stands for integral. Okay? When you integrate, you are doing the reverse of the derivative. Okay? There is an upper limit of your integration, and there is a lower limit of your integration. Meaning there's going to be some interval that you're taking the integration up. Remember, and the area under the curve is between 2 points. We've been doing between 0 and 4, 0 and 5. It could be, though, between 3 and 8. It doesn't always have to start at 0. And those represent our upper and lower limit. F of x, well, I mean, that's known as the integrand, but it's a function. It's whatever equation we're using. Remember we have 1/8 x squared minus 1 or something like that, or plus 1? That's the integrand. Okay. So, Kevin, who's not here, was like, can we do this in the calculator? Yes. So someone let Kevin know you can do it in the calculator, right? All right, and d of x is the variable of integration. Meaning, if you're using the x variable in your function, your integrand, then it's dx here. And it's also called the dummy. D for dummy. Because the answer does not depend on this variable thing. It doesn't depend on that at all. Okay? So, it's just part of the notation. Not too complicated. Not too complicated at all. Integrals are the reverse process of derivatives, okay? So, if, for the example on the left here for derivatives, if I want to find dy dx, derivative of 5x squared, what do? Yeah. I multiply by my exponent, right? God bless you. If I have 5x squared, I bring this down and it becomes 2 times 5x squared. That's when I multiply. And then what do I do to the exponent? Well, we're doing derivative now. No, we subtract 1 from the exponent. So now I have 2 times 5x to the 2 minus 1, right? Which is 10x. You guys should be able to do this in your sleep now. 10x is the first. You don't have to write the 1, but for this example, we will. So now there's an integral. And many things in math, but we got to do the opposite process. Not only do we do the opposite math, we do it in the reverse order. So meaning, if I want to integrate 10x, well, wasn't that my answer? Shouldn't I come, if I'm going to go backward from 10x, shouldn't I get 5x squared?
Yeah.
All right, well, what do you think I do? Yeah, and first I'm going to start by adding 1. See, I ended by subtracting 1, so instead of end, I'm going to start. And instead of subtract, I'm going to add. So, I've got 10x to the 1. I'm going to start by adding 1 to the exponent. So now I've got 10x squared. Now what do? Yeah, instead of multiplying by that exponent now, I'm going to divide by that exponent. So now it's 10x squared over 2. And what happens between my 10 and 2? The thing is, when you're reviewing, and you start doing it quickly, because you guys can find the derivative of 5x squared easy. Boom. When I ask you for the integral or integrate 10x, don't tell me it's 10. And take the derivative of it because you do it quickly. You just got to make sure you know which way you're going. Okay? All right? Okay? Okay? Bam! All right. So what does this mean? Now, just by knowing what do you have to take the derivative of to get a 4?
4x.
4x, right? So you really have to go through that process. No, I mean, you should know by now you had 4x, that gives you 4. So when I integrate that, all I'm going to do is, well, I'm going to integrate 4, right? And that should give me 4x. You're correct. Because technically I have 4x to the 0, don't I? I add 1 to the exponent to get 4x to the first. And then I divide by that. So I get 4x, okay? Now, well, so what is this? So this means right there, I just integrated it. But what does this mean? I have a bound. So if my graph, think of it this way. If I'm going to find the area under the curve, it's 4x, it's just goes through here and goes up by 4. I'm going to go from here 0, 1, 2, 3, 4. I'm going to go from 1 to 4. That's what this tells me. So I take, what do I want? I want all this area in red from 0 to 4, but what do I got to take out? I got to take out 0 to 1, don't I? So all I do is from 4 to 1, which means first I put a 4 in here for x, I take that value and I subtract, putting 1 in for x. So that means I take 4 of 4 and subtract 4 with a 1. Yes, it would be 1. Okay, so it's 16 minus 4, which is 12. So this whole thing would equal 12. Okay, so all this means here, all these numbers, these 4 and 1, these upper and lower limits, this means you're going to take the integration and put a 4 in there, and then take the integration and subtract a 1 in there. Okay? So here's 4 in my integration, and I'm going to subtract, here's a 1 in the integration. Once you get the integration, it's written like this in a line from 4 to 1, because you don't do this anymore, you already did that. Okay? That process is done. Now you just take it from 4 to 1 and just change the notation. Yeah, integration, that's one of the numbers. Sometimes there isn't. And if you were ever, and I'm not sure if I'm getting ahead of myself here or not, but let's say this integration here was like this. It's the integration of 4 dx. Well, if I integrate that, I know it's 4x, but what about the numbers? Well, if there's no numbers there, then you don't have to put anything in. It's just this. Yeah, there's no numbers to put in or subtract, it's anything. Okay? Yeah. All right? I'm going to give you a minute to work on this one at a time. Just like derivatives, you do one at a time. And they're minus in between those two, plus between those, from 3 to -1. Okay, go ahead and do it. All right, I saw some good things. Everybody was, if they weren't close, they were real close. Okay? So, I'm going to integrate this whole thing. First, I'm going to integrate this one. Well, I add 1 to the exponent, and then I divide by that exponent. So that becomes x cubed minus, well, I add 1 to this exponent, it becomes 2, and then I divide by 2. So it becomes, okay, this was x to the 0. I add 1 to make it a 1, divide by that 1, that's just 5x. That's the integration. You should have gotten that part. You guys are all good enough to get that. Now, I've got to take this from 3 to -1. And I want you to get the habit to do 2 things. First, when you input a number, put parentheses around it. 3 cubed minus 3 squared plus 5 times 3. Okay? That will take care of any negatives if you have any questions with negatives and positives. Now, it's that whole thing, and I want you to put brackets around, minus the same thing with a -1 in. So now you can evaluate both of them and just subtract them separately, okay? So I've got -1 cubed minus, and here's where the issue comes, minus a -1 squared. Some of you would have just taken a minus, put a 1, and made it a +1. That would have been the issue. -1 squared is positive, but you're subtracting that +1 here. Okay? Plus 5 times -1. Okay? I want you to get in the habit of doing this. So, this is 27 minus 9 plus 15 is 33. What do we got here? This is -1 minus a +1 minus 5, which is what happens when we subtract the negative? So this whole thing, before I made a mess of it, equals 40. The area, and let me explain to you what that means. The area under the curve of that function, from x is -1 to x is 3, is 40. Very aggressive thing on here. All right. Oh, I'm sorry. Yeah. Well, look, you can. I can take all these values and distribute the negative sign, that's fine. But I think it's much simpler to just figure out what this is and what this is and subtract. It's less to keep track of. You can do it. This, I distributed this. I get +1, +1, plus 5. Now I get 33 plus 7, which is 40. But now I've got to keep track of changing 3 signs instead of 1. See what I'm saying? There might be a sign or a cosine in there, and then it kind of, you know what I mean, to integrate it, just keep them separate, subtract them. I mean, as long as you get the right answer, I don't mind, but it's a lot easier to keep track of. Yeah. Speaking of sine and cosine, can I let you guys try this one on your own?
Yeah.
Yes. I'm going to take most of those no's as yeses.
I said yes.
All right, thoughts.
So, this.
Can you explain elaborate?
Because if we brought this back, there's a lot. Here's the integral of cos x to 1 is.
That's not for trig. That's only for. That's only for terms without trig in it. Just, well, what would give you cosine of x? You're right. Sine of x, that's it. That's sine of x. If I think about it this way, if you ever come in and you're not sure, if I can, no, stay up here, if you're not sure, well, what happens if I took the sine, you know, the square there, of x squared, or even, what happens if I did the sine of this? The derivative would be cosine of this times the derivative of the inside, right? So it would be 2x cosine of x squared. That's not what you started with. The derivative of just the sine of x would give you cosine of x. That's what you have, so that's what you want to go back to. Okay? If you're ever unsure, take the derivative of what you came up with, and you should get integrand, that function, okay?
Oh, that's
Yeah, that's a way to check it, absolutely, because y'all are pretty good with it. So no, finish it off. Sine of x.
alright, so that's sine of 270 minus the sine of 90.
Right, and we know that because 3 pi over 2 is 270. Pi over 2 is 90. Good, good.
So sine
What's that?
sine of 270 is
Negative 1.
and sine of 90 is 1. Alright. So when you have negative 1 minus 1,
Negative 2. Very good. Thank you very much. Good. Good. Here we go. Using geometry to make it easy, notice it says sometimes. We never really did an integration of the absolute value of x. But what does the graph of the absolute value look like? It's a v. Absolute value is a v. So, for poo-poos and ha-has, okay, if I go 0, 1, 2, 3, here's 4, and I go negative 2, I go 1, 2, 3, 4, here's 4 here. All right? And I can just find the area under the curve. Maybe it makes a perfect geometric shape that I can see the area of. In this case, it does. Okay? If I put a 4 in here, if my function, all right, is this. What's the absolute value of 4? It's 4. Over here. What's the absolute value of negative 2? It's positive 2. It makes everything positive, right? Down, then up. Okay, if I draw these two straight lines from the area under the curve, why don't I find the area of this triangle and the area of this triangle and just add them together? What's the area of a triangle? What is it? 1/2 base times height gives me the area of a triangle. This is 4, and this is 4. This is, we don't measure distance in negative. Even though it's going to negative 2, it has a distance of 2. This has a height of 2. So really, all I'm doing is I'm adding these two areas together. So I now have 1/2 the base times height, which is 4 times 4, plus 1/2 2 times 2. What do I got? Half of 16? And what's half of 4? There you go. There you go. Sometimes it's a lot easier. Bam. All right, here's another one. This doesn't seem obvious that it's a shape. This doesn't seem obvious that it's a shape, but if I graph it, half of a, it's half a circle. It's half a circle, which means, obviously I made this window 3 by 3, and I kind of made it a square instead of a rectangle like on your calculator screen. If it was a rectangle, I don't know that. If it was a rectangle, it kind of looked like that, which is weird. But when you straighten it out to make it a perfect square, it looks like a perfect square. So it is. So all I'm going to do to find this area under the curve, well, the area of a circle by r squared. What's my radius here? Well, it's 2. The area of the circle is 2. Measurement is never negative. Yes, this goes from 0 to negative 2, but that's a distance of 2. I traveled 2 to the left there. So guess what? Pi r squared, which is pi times 2 squared, which is 4 pi. Is that my answer?
No.
How come? It's half the circle. So I've got to take half of this, which would be approximately 6.28 something.
Yeah.
Now, that wasn't that bad. That's it. You see how sometimes it's a perfect geometric shape and it's so much easier? I mean, for you to make that exponent a 1/2 and then put that in parentheses, and that would be tough. That'd be cray-cray. If it would be. But I'm going to show you something to make your lives a million times easier.
So the answer is 2 pi.
2 pi. That's the total area under this curve, which is half that circle.
So if there's something like that in your graph, let's say 2 cubic squares, which is x.
Well, think about it. The area, or excuse me, the equation of a circle has a y squared and x squared, right? If I were to write this, y equals radical 4 minus x squared, and I wanted to get rid of that radical, what do I have to do? Bang, bang. Now I've got y squared equals 4 minus x squared. What happens when I add x squared to both sides? The center is 0, 0. That's the radius squared. The radius would be 2. There you go. Now let me show you guys something that's going to make your life easy. Everybody have a calculator?
Is it going to be like the E thing that you just went
Wait for it. Wait for it. Calculator, how we love thee. You ready? Hit the math button. That's always a good one. I hit the math button, there I am. Then, option 9. You see how option 8 was derivative? Option 9 is actually it means function integral, integration. That's fn int. Guess what happens when I do that? Look at how pretty that is. Man, why don't we do the one with the 2 triangles? The absolute value of x. That went from what? Negative 2 to 4? So I'm going to start down here, say negative 2, move up, that's going to 4. Everybody remember where the absolute value is? Math over 1 plus 1, bam, of x. Now, dx. What was our answer?
Why?
It's close enough. If you see 10.00000, because the calculator does method slightly different. It actually uses, I believe, Riemann Sum, and I might be inaccurate, as I know it's a recording. So there's always that little error of the little part that's above and the little part that's below when you take what's the right corner, left corner, the mid. Okay? So let's do another one. Let's do that circle one. Or let's do, what was that one? 3x squared. So if I go to math and go to option 9, what was that from? Negative 1 to 3? Okay? And what we're doing is this one right here. Oh, you do the cosine, we'll do this one. We do trig as well. Okay? And that is 3x squared minus 2x plus 5 dx, right? What was our answer?
40.
40. There we go. Yeah.
Would you suggest doing the belly of the calculator before you do this in case you stored something with your
Before I always do big stuff, I always clear the memory. Because you don't know what to ask. This doesn't matter. This doesn't matter here. Yeah, that's insignificant. And you're not actually taking what's stored into x here. You're going to find a derivative of this, and then you're going to actually plug these into x. So you're telling what to put into x. It's not going to retrieve what's stored into x, the last thing. But I always clear the memory. Before each class, I clear the memory, so, you know, it's a little bit better. So that makes life easy, doesn't it?
Yes.
That would work for anything, even the trig one. There are some multiple choice questions that are like this. This is simple enough. You can do that without a calculator. There won't be a calculator for this. But if it was complicated, like it might be like outline of whatever, blah, blah, blah. Got a new calculator, all right? Good job, guys.